Welcome to DP Tutorials by Donny Jerwa. In this teaching module, we will emphasize and accentuate on deriving an expression for the internal resistance of the cell in terms of the EMF of the cell and its terminal potential difference. So let us reiterate on some of the terms that we have discussed in the previous lecture. When we have a cell, in this form, one terminal of the cell, which is the electrode, will be positive, and the other terminal of the cell will be at a negative potential. This terminal of the cell, which is at a positive potential or the positive electrode, we define as the anode, and this terminal of the cell, which is at a negative potential, is defined as what? Is defined as the cathode. Now, eventually, when the circuit is closed, current will flow in throughout the circuit, and always the charges will move from when the current flows in a circuit. That means it always moves from the positive terminal of the cell to the negative terminal of the cell. And when you measure the potential between these 2 points of the cell, that potential difference is what is known as the terminal potential difference. And the EMF of the cell is nothing but the potential difference of the cell in an open circuit. So when we have a cell in this form, that means due to the obstruction of the movement of charges from one end of the cell, from the positive to negative, it will give rise to the internal resistance of the cell. So the internal resistance, any resistance attached to the cell, this is known as your internal resistance denoted by R. Some representation used to refer in that form, and some representation will be in this form. We have the cell, and then we draw internal resistance which is below the cell. So this indicates that this is what? This indicates that this is our internal resistance. Okay? This indicates that this is our internal resistance R. Okay. So from here, the EMF will be E of the cell. Mind you that the EMF E of the cell is always greater than the terminal potential difference V of the cell. So over here, we have the cell having EMF E, and let R be the internal resistance of the cell. And in the circuit diagram, okay, we have this load resistance capital R, which is connected across the 2 terminals of the cell. One terminal of the cell will be at a positive potential, the other terminal of the cell will be at a negative potential. Now when this is positive and this is negative, and when we have a key, let us place a key over here. When you have this key, that means this is an open circuit. The moment when I put a dot or I insert a plug, that means that circuit is the closed circuit. In a closed circuit, current will flow. Okay, current will flow, and when current flows, that means part of the current or this current will be moving in this direction. The current will be moving on that direction, and when current flows, it will always flows from positive to negative. Let I be that current. Okay, current in the external circuit. So from here, the E is the EMF of the cell, R is the internal resistance of the cell. That is why we have enclosed this internal resistance of the cell by using this dotted bracket, dotted square rectangular shape, which indicates that this R is not the load resistance, this is the internal resistance. We have indicated like this, it means then that R is the internal resistance. Okay, this capital R is what is known as the external resistance, or we define that as the load resistance. So it may be noted that the EMF E of the cell is always greater than the terminal potential difference V of the cell. So from here, if you want to find out the potential difference between these two terminals, positive and negative of the cell, so you have to connect across a voltmeter. So if this is positive, that means that end of terminal of the voltmeter will also be positive, and this will be negative. So from here, from this circuit, if you want to find the current, okay, the current will start flowing. So if you want to find this current, when the circuit is closed, current will always be determined. So when the circuit is closed, current starts flowing. And this current starts flowing in the circuit. The current will be given by this expression. The EMF E of the cell divided by the total resistance. Total resistance will be internal resistance plus the load resistance. Or in this case, I can write as external resistance. Okay? External resistance plus the internal resistance, which is the load resistance. That will be the value of total resistance. That will give us our total resistance. So it will be load resistance will be capital R, internal resistance will be small r. So in this case, we will get I equal to, our cross multiply the denominator to the left hand side of that equation. So it gives us this expression. It gives us this expression, and from here, that means we get a term in that form. So we get this expression plus IR, which is equal to 1, which is equal to V, which is equal to E, the EMF of the cell. Now, we also know that by using Ohm's law relation, okay, it is evident that this IR term is nothing but the terminal potential difference. Okay? That IR term is the terminal potential difference across this load resistance. So this V equal IR, this is the terminal potential difference, or we define this as what? As the voltage. Okay? As the voltage across what? Across that load. Okay? Across that load resistance R. Across the load resistance capital R. And what is this IR? IR is basically, okay, IR is basically that small IR is nothing but the potential via one, via the cell, okay, via the cell. So that IR, small I and R, this term, this will be the potential, okay, across the cell. So let us mark this as equation number 1. Okay, when we mark that as equation number 1, equation 1 reduces to, okay, equation 1 reduces to, it means over here this will be capital V by making use of this expression. This expression comes from what? Comes from Ohm's law relation. Okay, V plus IR, this will be equal to what? This will be equal to E. Okay, this will be equal to E. But now, from here, that means this IR, okay, this IR will be equal to what? Will be equal to the EMF E of the cell, EMF E of the cell. Take this V to the left or to the right hand side, then you get negative V. From here, it implies, from here, it is very, very important. Okay, from here, it is very, very important to note that this EMF E is always greater than V. Okay, it is proof from this relationship. Okay, from that relation is very, very evident and clear that the EMF is always greater than the terminal potential difference. So from there, okay, let us solve further. We also know that since V equal I capital R, the potential drop across that load resistance, so we can write I, okay, we can write I, the I will be equal to what? V divided by R. So replacing this I by V divided by R, we can find out what is small r. So this is I, and this is your EMF, and this is the terminal potential difference. So we can find out small r. What is small r? Small r in this case, okay, small r in that case will be equal to 1. will be equal to E minus capital V. Okay, cross multiply R and cross multiply V the side, so V will be over here, and this will be 1. This will be into capital R. So this is the expression. Okay? This is the expression for the internal resistance of the cell. Okay? This is the expression for the internal resistance R of the cell, which gives, okay? This gives the expression for the internal resistance of the cell. This gives the expression. This gives the expression for the internal resistance. Okay? Internal resistance of the cell, in terms of what? Okay? In terms of what? In terms of the EMF E of the cell and the terminal potential difference V. So keep in mind that this derivation is important from examination point of view, and it will be around preferably probably 2 marks or 3 marks question. And another point that we need to ponder upon is some of the notes below, which I have written that during charging of a cell and during discharging of the cell. What happens during charging of a cell? During charging of the cell, remember that the EMF of the cell, the EMF of the cell is given by some expression. The EMF of the cell is given by some expression. If you look from this equation, this equation is the foundation. This equation is that foundation for the node number 1, which means that this happens during charging. During charging. So during charging of the cell, the EMF of the cell is given by this expression, which means that the terminal potential difference plus the voltage drop across the cell will be equal to what? Will be equal to the EMF of the cell. And during discharging, when we are talking about discharging, that means we will have the expression from here, from this relation. If we take for the discharging, when it's discharged, that means you want to find the terminal potential difference. So during discharging, that means over here the EMF of the cell will be equal to 1, will be less than the potential difference of the cell. So this V equal E minus IR. This will be the case. During what? During discharging. This will be for during discharging. When I say during discharging, that means current is flowing in the circuit. Current is flowing in the circuit. During charging, no current is flowing in the circuit. So from here, making use of those two expressions, that means during charging, the EMF E of the cell, is given by this expression, V plus IR. So remember this expression. This expression is very, very important. And V is the terminal potential difference of the cell, and IR is the potential drop due to the resistance of the cell. And then another important point is that during discharging, this is the expression. The terminal potential difference, the terminal potential difference V is equal to what? Is equal to the EMF of the cell minus the potential drop due to the resistance of the cell. So keep in mind that EMF E of the cell is always greater than the terminal potential difference V of the cell when the cell is in a closed circuit, or when current is flowing in the cell. What happens? Suppose if I study that for the case when there is no current is drawn from the cell. I have a cell like this, and there is no current which is drawn in the cell. What does it physically mean if I have a key like that? If no current is drawn from the cell, that means current I, if no current is flowing from the cell, it physically means that I will be equal to 0. Yes or no? I will be equal to 0. If I equal to 0, what does it mean? It means that the cell is what? The cell is said to be what? The cell is said to be open. Okay? So when no current is drawn from the cell, or when no current is drawn from the cell, the circuit is said to be open, and in such cases, the current I will be equal to 0. If current I is equal to 0, if you place on this expression, suppose if I mark this as relation number 2, and if I mark this as relation number 3, you will find out that if you put I equal to 0, E will be equal to 0. If you put I equal to 0, even the EMF of the cell will be equal to what? Will be equal to the terminal potential difference of the cell. That means from both cases, from both these expressions of 2 and 3. What does it mean? It means that the terminal potential difference of the cell will be equal the terminal potential difference of the cell. I mean the EMF of the cell. The EMF of the cell will be equal to the terminal potential difference of the cell, provided if no current is drawn from the cell. If no current is drawn from the cell, so this expression will hold true. Okay? Will hold true. So what is EMF of the cell? EMF of the cell is that potential difference of the cell in an open circuit. Terminal potential difference of the cell is the potential difference in a closed circuit. Current flows in a closed circuit. Current does not flow in an open circuit. Current flows in a closed circuit. Current does not flow in an open circuit. So what is this EMF? Let's just reiterate. Let us revise. The EMF of the cell is nothing but the work done on moving a charge in order to drive once around a closed circuit. And the terminal potential difference of the cell is the work done on the unit charge, driving in from the positive to the negative terminal of the cell through the external load. So you just go through those derivation so that you will understand the analysis of all these important terms. So from here, remember that during charging is given by this expression, and during discharging it is given by this expression. Okay? Thank you.